Hello everyone, in this video, I will explain how Fourier transform infrared spectroscopy work. To really understand how FTIR works, we first have to understand one simple idea. Waves interfere with each other. Let's start by looking at this figure. When two waves overlap, they can either add together or cancel out. If the peaks line up with peaks, the result becomes a bigger wave. This is called constructive interference. But if the peaks of one wave line up with the valleys of another, they cancel out, giving destructive interference. You've probably seen this in real life without realizing it. Think of ripples on a pond. When two sets of ripples meet, sometimes they make a bigger splash, and sometimes they flatten each other out. Light behaves the exact same way, and this idea of interference is the heart of Fourier transform spectroscopy. Now, let's move to the second figure, which shows the famous Michelson interferometer. This is the key optical engine inside every FTIR spectrometer. It may look complicated, but the idea is simple. Light from the source hits a beam splitter, which divides it into two beams. One beam travels to a fixed mirror, and the other travels to a moving mirror. Both beams hit their mirrors, bounce back, and return to the beam splitter, where they recombine. The magic happens here. Because one mirror is moving, one beam travels a slightly longer path than the other. When the two beams meet again, their waves overlap, sometimes adding, sometimes canceling, depending on the difference in distance they traveled and the wavelength of the light. Every wavelength interferes in its own unique rhythm. Short wavelengths oscillate rapidly as the mirror moves, while long wavelengths oscillate more slowly. As the detector watches the total intensity of this mixed signal, changing with mirror position, it records a pattern called an interferogram. At first glance, the interferogram just looks like a messy wave, but hidden inside it is the contribution of every wavelength coming from the source. This brings us to one of the most beautiful ideas in spectroscopy. Instead of separating wavelengths physically using a prism or a grating, FTIR encodes all wavelengths at once into the interferogram, and then uses mathematics to decode them. By the way, it's good to quickly remind ourselves how prism or grating work. As you may know, a prism separates colors because different wavelengths of light bend or refract by different amounts when they enter and exit the glass. Shorter wavelengths bend more strongly, and longer wavelengths bend less, so the prism literally spreads the beam into a rainbow by slowing each color differently. A diffraction grating, on the other hand, works by interference. It has thousands of tiny, evenly spaced grooves, and when light hits these grooves, each groove acts like a tiny secondary source. The waves leaving the grating overlap with each other, and depending on the wavelength, they interfere constructively at specific angles. This is why gratings create those sharp, well-separated spectral lines. So while prisms separate wavelengths by refraction, gratings separate them by interference. Both devices split wavelengths in space. We physically point the detector to a different angle or slit to read each wavelength. FTIR avoids all of that. Instead of physically spreading the colors apart, it lets all the wavelengths hit the detector at once, but in an encoded form. A computer performs a Fourier transform to mathematically extract each wavelength from the interferogram, much like recognizing individual musical notes inside a chord. Once you understand that, the advantages of FTIR make complete sense. One of the biggest strengths is the Jacquinot advantage, named after Pierre Jacquinot, also called as high throughput. Traditional dispersive instruments need slits and gratings to isolate one wavelength at a time, and those slits block most of the light. FTIR, on the other hand, doesn't need any slits, so much more light reaches the detector. More light means a better signal-to-noise ratio, which means clearer, more reliable measurements. Another major strength is the Felget advantage, also called the multiplex advantage. A dispersive instrument has to scan one wavelength at a time, but an FTIR measures all wavelengths simultaneously in the interferogram. This makes data collection much faster and improves sensitivity for the same measurement time. And then there's the Kahn's advantage, named after Janine Kahn, or high wavelength precision. Instead of relying on the mechanical accuracy of a grating or prism, an FTIR uses an internal laser reference inside the interferometer to measure mirror displacement with incredible precision. That gives extremely accurate and reproducible wave number calibration, so FTIR spectra agree from instrument to instrument and lab to lab without constant recalibration. In the end, the story of FTIR is the story of how a simple idea, interference of waves, combined with brilliant engineering in the Michelson interferometer, created a technique that is faster, more sensitive, more precise, and far more robust than older dispersive IR instruments. Instead of splitting wavelengths apart in space, FTIR encodes them in time and lets mathematics do the rest. That's why today, almost every modern infrared spectrometer you see is an FTIR.